Okay, gentlemen, we started that chapter regarding thermodynamic principles related to open systems. Okay, and particularly we are interested in the first law of thermodynamics. Before going for that first law, we talked about mass flow rate, I think, and I just gave you some hints about the practical application. Why do we need to introduce those ideas? And we also talked about law of conservation of mass at that time. Okay, so whatever the coming in, it is going out, and that should be equal to the mass which is coming in and the mass which is going out. That's a combination of this combination is equal to what? The change in the mass of the control volume. Okay, so we looked at its different forms, and those forms include the differential one and the integral one. Now we are going to talk about the conservation of energy for a control volume. Yeah, this one. So conservation of energy for a control volume. And before going for its mathematical form, you can just see this is kind of a control volume. Okay, and this dashed line is representing control surface, which is basically a boundary for the control volume. Now you can see that energy can be transferred to this by heat and work. Even if you talk about the closed systems, this is there, this W term and this Q term is there. Okay, and what is the additional thing? Additional thing is that mass is coming in and then mass is going out. Okay, so whenever you are bringing mass into the system, so that system is basically what? So that system is bringing some kind of energy into it. Okay, that mass is bringing some kind of energy into the control volume. And once you transfer the mass from the system to the environment or just outside the control volume, you can say that obviously it would also take some heat or some energy away from the system. I would say some energy away from the system. Okay, so we need to add those terms. Generally, whenever we write down the first law of thermodynamics for closed systems, what we say is time rate of change of the energy contained within the control volume at time t So whatever the changes occur in the control volume's energy, that would be equal to net rate at which energy is being transferred in by heat. And obviously, because it's a transient process generally, so we say that it is at time t. And then the next term would come from the work. Okay, so that would be net rate at which energy is being transferred out by work at time t. And I told you what's the additional term. Now to this extent it is applicable to both the closed systems and the open system to this extent, but for closed control volumes, the open systems, you have to introduce a new term which belongs to the mass transfer. Okay, so that mass transfer term, I just spell it as the net rate of energy transfer And by the way, I'm just writing down into, but obviously it is equally applicable to that mass which is going outside. Okay, so just the sign would change. So into or out of the control volume accompanying mass flow. Okay, now if you see those terms, whenever you transfer fluid, or if you talk about motion of a fluid, there are basically how many types of energies are there which we talked about last time? We talked about internal energy, we talked about kinetic energy, and then potential energy, if you remember. Okay, so if you look at this mass flow rate, this UI is what? This is internal energy per unit mass. This VI square by 2 is what? You define kinetic energy as if it is mv square by 2. So if you divide it by m, it would give you v square by 2. Simple as that. And then if you talk about let's say potential energy, come to the seat. Yeah. And finally we talked about the potential energy, and that potential energy generally it is what? It is mgh. Okay, and h is basically what? It's the height from some reference ground or some reference position. Generally we call that reference as datum. Okay, this is the word which you would see in your fluid mechanics course as well. This is something which is known as datum. Okay, datum is something which you take as a reference. Okay, so the height from that datum, it would give you that h or z. Generally we use h symbol for enthalpy, so we would use z symbol for that height. Okay, if you divide it by m, again you would get gz, right? So whatever that energy is associated with this mass going inside the control volume, it's a combination of what? Internal energy per unit mass, kinetic energy per unit mass, and finally it is what? It is potential energy per unit mass. Okay, and the same is true for this mass which is going outside, right? So you can say that's a term which is there, and that we need to basically associate it with the mass flow rate, and that is only applicable for those systems which are open, which are basically represented by the control volume. So let me just write down its mathematical expression. So if we just talk about one inlet, one outlet, to this extent it is applicable to both the systems. Closed system, you already know that, and then finally we have to incorporate this thing. Okay, and if I just consider it as inlet or exit, so this would be inlet and exit. Okay, sorry. Okay, thank you. So this is something which is there. So that's the form of law of conservation of energy, or you can say first law of thermodynamics for what kind of systems? Control volume type of systems, or which are basically known as open systems. Now I hope you understand where this m dot is coming from, because we are talking about rate of change of energy. So if you multiply each of these terms by m, then you would be able to get the internal energy, and then kinetic energy and the potential energy. And obviously there is a dot because we are talking in terms of rate of change. Okay, now this point is quite interesting. Generally you are able to define all those terms except work. Whenever you talk about work, again it is very important to understand, whenever you talk about work, it is composed of two types of work. Work, it is basically what you can say, we classify it into two types. and those two types, one is known as flow work, which is there due to pressure and velocity. And the other classification is basically it includes everything, whether it is a shaft work, just like you do in the turbine. If you remember, we talked about the turbine last time, that turbine rotates and with the shaft it transfers its energy to the generator. Okay, so this is kind of a shaft work, the work done by the shaft. Or you can say there can be anything which, or there can be any work which is there due to change in the boundary of the control volume. Or you can say from the conversion of one energy form to the other form. It can also include that work. Electrical effects or magnetic effects or whatever it is. Okay. Now for different applications, with the passage of the time, I think starting from this lecture and the next lecture, we would talk about these work types as well for different applications. Just like for pump, what kind of work you should consider, for nozzle, what kind of work you should consider. Similarly for turbines, or let's say you talk about heat exchanger or any other thing, we will talk about that. But my point is, this work is classified into kind of two types. One is flow work, which is related to pressure and velocity, and the other one is shaft work, which is change in the boundary of the control volume or electrical effects. Okay. Now the point is, how do you define flow work? I'm sorry? Can both work what? No. Flow work would always be there. Whenever mass is coming in, obviously that flow is there due to what kind of pressure difference. Whenever there is a pressure difference, there would be a fluid flow. Okay. Now the point is, if you talk about a nozzle, let's say, I would talk about that nozzle as a case study in I think after like 10-15 minutes, you would see that you are talking about a nozzle. Now the mass is coming in and mass is going out. Simple. Are you transferring some kind of energy as a through the shaft to some other system in case of a nozzle? For example, just look at that. My point is, yeah, this one. This is the nozzle. Flow is coming in, flow is going out from this side. Is there any kind of shaft work included? This rotation of a shaft, or let's say displacement of some kind of boundary? Not at all. So it means the second work type is what? It's zero in that case. But for turbine, if you have a turbine, obviously you know that there would be a turbine, there would be a shaft associated with it, and then this shaft, due to its rotation, it would transfer its energy to the generator, and as a result that generator rotates, and then it goes on to the next electricity supply system. Now, is there any kind of shaft work for turbine? Yes, so it means the second work type is not zero, right? So we were talking about that flow work. By the way, I would just give you a small hint. I won't go into the detailed derivation, but I can just tell you, for example, if you just see this, just see this system. For example, this is the system, this is control volume. Now if there is, just consider this is a small mass, fluid element, you can say, I would call it as a fluid element. So for example, if I want to push that fluid element into the control volume, I just want to define work, flow work. Flow work is basically what? It's a combination of pressure and velocity, right? And how you can see that? What is the, basically you can say, what is the physical significance of that flow work? Just consider it's my control volume and it is something which is a fluid element. Now at this inlet, this is the inlet of that system. and this is the exit of that system. For example, if you want to push that fluid element into this control volume, you need to do some work, isn't it? And obviously that work would be what? It's a combination of force and displacement, isn't it? How do you define work? It is force into displacement. Now can we relate force with the pressure? It's pressure into area, right? And then if force is pressure into area, I know that to how much extent I need to push this. Like for example, if I want to push this fluid element into this control volume, this has to be traversed by a distance of L, isn't it? So you can say that this is force, and then it is, do you understand that? Do you agree or not? I hope I have communicated my point. So the point is, what is it? Is it a kind of volume? Is it a kind of pressure? Now if I just divide it by T, what would it be? Come on. Oh no, I'm sorry. This is force, and now this has become work. This has become work. So this work divided by T, if you talk about this rate of change of doing work, what would it be? It would be PA, and then this would be dl by dt is what? It's velocity, isn't it? It is what? It is velocity. So you can say now that's how you relate. This is the flow work. The flow work is what? Physically, if you see this term, it is something which you are putting in to push the fluid element into that control volume. And then if you similarly, if you look at the exit, so that is something which you have to put in to what? To extract that fluid element out of that system. Okay, so this is something which is flow work inside the system and outside the system. So anyways, this is how you define it. So I would say that this work done is basically equal to work done due to the other type, due to the second type. I would represent this work done as W dot CV. Now what do you mean by CV? That is something which is done by the control volume itself, by changing its displacement, by some kind of shaft work, by some kind of electrical energy, right? So that other type of work is basically being represented by this thing, W dot CV. So CV is basically for control volume, and the other type of work is basically flow work. Okay, and this flow work is what? This flow work is a combination of pressure, area and velocity. Okay, just look at that. There are two types of work. I told you, one is this one and the other one is this one. This W dot CV is used to represent this one. If there is some shaft work, you would say it is being done by the control volume itself, right? And that W dot CV is there, right? So this is flow work. Now this flow work is because this flow work interaction occurs both at the inlet and the exit. So what I can see is this W dot, I would represent that W dot as W dot CV plus PE, VE, AE, and then PI, VI, AI. Okay, it depends. That positive negative sign are quite clear to you. When do you put a positive sign? When do you put a negative sign? Right? So just use those signs effectively and depending on the physics. Now see, these two things are what? Flow work at the inlet and at the exit. This term includes what kind of work effects? Shaft work, some kind of displacement of the boundary, and then it can be due to electrical or magnetic effects. Okay. And similarly, if I want to represent in the specific volume kind of representation, what I can see is, I would see that this W dot would be equal to W dot CV. Okay, so this is W dot CV, and finally if I just represent it as if it is M dot PE VE minus m dot I PI VI. Now I have converted that volume or velocity. Just see what is that. What was that? That was what? Just think of it. That was volume divided by time. That was volume divided by time. So if we just represent it in terms of mv and then divided by time, so it would give me what? M dot specific volume. Okay, these things are equivalent. Yeah. Thanks for that correction. Yeah, this one is velocity. Yeah, just look at that. What was that? Initially we started off with PA and then L we divided by T and then we say it is dimensionally a velocity. So basically this area, sorry, what? Okay, just see. This was what? This was work. If I just divided by T, it would what? P or what? This is W dot. This is something which is, can I say this would be PV volume divided by T? What is that volume? Can I say this volume would be what? Specific volume into mass over T. Can I say that this would be something which is like this? Right? So initially I wrote it down this expression. This was PAV and this V is velocity. Okay. Now it means if we just write down the first law of thermodynamics in its original form, first law of thermodynamics, so what was that? This would be D. That was Q dot. What was the second term? It was W dot, and then W dot was what? It was divided into two terms, and those two terms include W dot CV and what? M dot PVE. Sorry, M dot PV. So then I can just say, I can just combine it with the other terms, and I can say this is UI plus PI VI plus VI square by 2 plus GZI minus M dot E UE plus PE VE plus V square E2 plus GZE. Now can you see that? I just plugged in all the values, the work done by the flow, which is the flow work, and the simple control volume work back into the original equation, and I just came up with this one. Now see, do you remember this kind of combination which we talked about? This is something which is enthalpy. Remember, enthalpy is not any kind of energy. Remember that. Enthalpy is not an energy term. It is what? It is just introduced for the mathematical convenience. That's it. And what is the mathematical convenience? That you can just add those two things into one form and you can just say, okay, we have one new term, just like you say C equals A plus B. Just like that. Okay, so it is just for the sake of mathematical convenience, you can say. So we can say that this H, which is the enthalpy per unit mass, that is something equals what? Internal energy plus PV. That's it. So remember, whenever you talk about enthalpy, don't think of it as if it is a form of energy. Energy is what? Internal energy is a form of energy. Enthalpy is not a form of energy. It is just there for the matter of convenience. That's it. Now gentlemen, if we have more than one inlets and more than one outlets, what would you do? You will simply add that sigma sign over there. Okay, so this is for more than one inlets and more than one outlets. That's it. And for example, if I say that we are talking about steady state processes, which term is going to be 0? This term would be going to 0. Okay, whenever you talk about a steady state process. I hope you understand that. Any questions? Now, gentlemen, let's talk about the integral form. I would just write it down over there and you can understand it yourself. By the way, I don't think there should be any problem with the expression because it is quite straightforward. You can define this energy as if it is this is basically specific energy. You can call it as if it is a specific energy. And what that combination of rho and dV would give you, that's the mass. Okay, so rho E dV integral, that would give you total energy. And I can represent this as rho just like this one. That energy can be decomposed into three parts: internal energy, kinetic energy and potential energy. If we use that expression back into the original one, I would just write down the final form. That final form would give me d by dt Now, can you interpret this one? Those first two terms, simple. This term is very simple again to understand. Just talk about this one. Can you understand this one? That U plus PV expression has been converted into H. Then you have V square by 2, then you have GZ, and finally you have what? What that term is? Integral of rho V and dA, what is it? It's simply mass flow rate, isn't it? It's simply mass flow rate. Okay, so you need to see the given input and then you can use accordingly whether you need to use the differential form or you need to use the integral form. Okay. Now, gentlemen, if you talk about the steady state, I have already told you, if you just talk about the steady state processes, both the terms, in the law of conservation of mass or law of conservation of energy, that would be what? Those left hand terms would become 0. Okay? And most of the time, remember, although processes are transient in nature, generally, but most of the time you would see that if the effect of those fluctuations due to time in any property value is very small, we can consider that process as if it is steady state. Like for example, if I just plot a graph in front of you and I say that there is some quantity x, you plot it with respect to time. For example, there are small variations and you see that its average is somewhere here. For example, this white line is just describing its average. Now, do you think that fluctuations are very small? I think we can consider that. So, if the fluctuations are very small, I can take that process as if there is no change happening with respect to time. Right? And see, what is the advantage? The advantage is we can get rid of so many differential terms with respect to d by dt, all the terms, if we consider any process as if it is a steady state process, so all d by dt terms would become 0. Simple as that. Okay. So just see that by introducing a small assumption, again not at the cost of accuracy. If you can say the margin of error is huge, you should not go for that. But if the margin of error is very small, you should consider that. Why? Because you are avoiding what? Huge mathematical complexity. So if those kind of fluctuations are involved, very small, you can consider that process as if it is steady state. Okay. How what? So now let's talk about those systems, the case studies related to different systems. I would solve few examples in front of you and we would talk about the working principle of why do we use nozzles, diffusers, or let's say pumps, turbines, why do we use that? I would just give you a small hint because the details of those systems you would study in your Thermodynamics II course. I won't go into that detail, but still you will have some idea and you will come to know how to apply that first law of thermodynamics onto those systems. Okay, let's talk about that. So let's start from the nozzle. Okay, quickly I would just move on to that. This one, no, not this one. Let me just. Yeah, this one. So nozzles and diffusers. You might have seen those kind of structures installed in front of your pipes. Now whenever you keep your hand or you keep your finger in front of a pipe outlet, what are you trying to create? You want to increase the velocity of the flow. But why do you keep your finger to block some portion of the outlet of the pipe? To decrease the area. And to decrease that area, what you are trying to do? You increase the velocity. Now why do you think that decreasing the area would increase the velocity? Why do you think that? Yeah, exactly. The amount of mass coming in needs to go out. Like for example, just look at this one. If you are considering a rigid body whose boundaries are not flexible, it would maintain its shape. For example, this is the mass which is coming in, or the mass flow rate coming in equals 2 kg per second, for example. That 2 kg per second should have to go out, isn't it? What is that? Is it equal to rho AV? Would it be equal to rho AV? Rho would remain the same because the liquid is incompressible. Okay, rho would remain the same. Liquid would remain incompressible. If area decreases, if area decreases, velocity has to increase so that both of those two quantities are equal. And if both of those two quantities are not equal, what does that mean? If mass which is going out is less than the mass which is coming in, it means that that structure is storing the mass, isn't it? Now, because you don't have any place to store the mass inside that nozzle or inside that diffuser, whatever is coming in has to go out. Okay, so if it has to go out, it means if you are decreasing the area, velocity needs to increase. So, gentlemen, this is something which is known as a nozzle. This kind of shape is known as a nozzle. And if you increase the area, like for example, this is inlet and this is outlet. This kind of structure where the inlet area is smaller and the outlet area is larger, this kind of structure is known as diffuser. And as a result of it, what you are trying, why do you increase the area and decrease the area? Because you need to control the velocity. And remember, velocity is related with pressure. Velocity is related with pressure. Remember that. If you increase the velocity, pressure would decrease. Now, just keep this thing into your mind. I would try to explain it. Once we move further, I would try to explain it. When you increase the velocity, pressure would decrease. If you decrease the velocity, pressure would increase. Just remember this thing, that pressure is kind of, not always, it's not a thumb rule, but for the basic fluid mechanics studies, just keep it into your mind. I would try to explain it once we move further. If the area is what? Okay. So a nozzle is in a diffuser, the gas or liquid, they just decelerate in the direction of flow. Okay, and in some way or the other, again I am not going to explain it, why does it happen, but just keep this thing into your mind that if velocity increases, pressure would decrease. If velocity decreases, pressure would increase. Just keep it in your mind. Okay. Now, why does it behave like this? We will talk about that, or you can have the detailed explanation in your fluid mechanics course. I would try to explain it as we move further, but let's see. Okay. Any question? Like let's come back to this expression. Just look at that and tell me which terms can be neglected. If we talk about the nozzle flow, the first thing is for the nozzle flow, because just see, it's a small nozzle. The area is very small. Sorry, not the area, by the way, the length of the nozzle generally is very small. So you can say the flow quickly passes through it. Right? The flow quickly passes through it. So if the flow quickly passes through it, can I say that there can be negligible heat transfer which is occurring with the environment? Can I say that? If it just passes quickly through that nozzle, I can say that, okay, fine. Is there any kind of shaft work in? Not at all. So it means WCV terms would also be zero. Now tell me, let's talk about this term. Do you think any similarity between those two terms GZI and GZE? Z are the same, by the way. Z are the same. If I just look at this nozzle, for example, and I just see that this is the center line, so that center line remains the same till the time nozzle is kind of tilted. If the nozzle is horizontal, Z1 would be equal to Z2. So you can say those two terms would also be cancelled. Okay. Any other thing, by the way, this term is going to be 0. This term is going to be 0. Right? So finally I would come up with something that the nozzle equation, first law of thermodynamics for the nozzle flow can be written as do you understand that? Any question?